In this second lecture, we will discuss popular semantic segmentation networks. Here, these are asked to do more than just find an object in a scene. Rather, they need to label every pixel or voxel as belonging to a class. To do this, they use encoder-decoder structures, where the encoder corresponds to what we've already seen for classification and regression, and so easily could also have residual or dense connections. Its goal is to detect objects in the same way as for a regular classifier. The decoder then wants to upsample these predictions from the very coarse scale afforded by the large receptive field size of the bottleneck back to the resolution of the original image to produce a dense, pixel-wise labeling of the scene. The first segmentation network we will look at is the fully convolutional network, which we also looked at briefly last week. So this was proposed in 2015, and it was the first to suggest swapping fully connected layers for convolutional layers. The reason why this is important is it allows the result to be upsampled back to the original image size in order to return dense predictions of all pixels corresponding to an object. These objects are learnt during training by presenting cropped patches from an image corresponding ideally to whole objects, where a further advantage of using convolutions instead of linear layers is that since these do not hard-code the required spatial dimensions of the input, images of any size may be passed at test time, supporting coarse-scale labeling of all the different types of object in a single scene. Thus, the encoder may be seen as detecting what is in the scene, and the decoder is mapping this back up to the original image resolution to detect where all the pixels corresponding to this input may be found. Where for fully convolutional networks, upsampling is performed through learning transpose convolutions. And since labelings learned by the encoder are a very coarse scale, for example shown here for this man on his bike, skip connections were inserted to put back in high spatial frequency information, otherwise known as the edges, by summing the output of the transposed convolution with the activations learnt by the encoder at the same resolution level. So for here, pool 4, and here, pool 3. So before we move on, let's discuss exactly what is meant by a transposed convolution. Transposed convolutions are seeking to learn the upsampling operation by optimizing weights of an upsampling kernel. Here, a 2x2 kernel labeled with the parameters T1 to T4, and this is applied to a 2x2 image with values 0, 1, 2, 3, and the goal here is to upsample by one dimension to a 3x3 grid. So this is achieved by multiplying each element of the image with all elements of the kernel so as to fill a 2x2 block of the desired output grid. For example, here we show all elements of the kernel multiplied element-wise with the top left element of the 2x2 image. And this then fills the top left block of the output grid. And again for the top right block and the number 2. The final upsample is then estimated by adding all overlapping blocks estimated from these operations to return the final result. So we sum the top left, the top right, bottom left and bottom right, seeing that these centre elements represented by this cross are overlapping and summed together. The problem, therefore, with transposed convolutions is that this way of combining kernel outputs leads to a checkerboard artifact as shown here. So it's possible that you might find taking an alternative strategy of upsampling and then following this with one or more convolutional layers, not shown in this diagram, may work better for you. Options for upsampling strategies include nearest neighbour interpolation, where you might imagine putting the existing map at the centre of a larger grid and then assigning all points on the output grid the value closest to them, say 1 for the top left, 2 for the top right. On the other hand, bilinear interpolation, or what would be trilinear interpolation for 3D, estimates the value at each output grid from a weighted average, where here distance provides the weighting. This is probably the approach that I would recommend. Also, and I think this is more common in methods for network interpretation, which we will cover in week 5, you could max unpool. So this saves the mask from the pooling operation through the encoder to propagate the values back during decoding to the location which was max of the operation at that level, Upsampling through interpolation followed by convolutions is indeed the approach taken by the very popular UNet architecture. So this proposes an entirely symmetric architecture for encoder and decoder, in both cases applying several convolutional blocks at each resolution level. It's this symmetry that gives it its U-shape. In the original network, the encoder applies blocks of 3 valid convolutions, therefore without padding, followed by max pool, with kernel size 2 and stride 2 for downsampling. Decoding is then implemented by upsampling through interpolation, and then importantly, the activations from the corresponding layer of the encoder at comparable resolution are first cropped to the exact same spatial dimensions and then concatenated, implementing therefore skip connections similar to the fully convolutional network, which have the purpose of propagating high-resolution features from the encoding path directly into the decoder in order to support capture of high spatial frequencies. Then, the convolutional layers of the decoder also learn a large number of feature channels, which allow the network to propagate contextual information up to higher resolution layers, whilst at the same time reducing a number at each level to match the shape of the encoding path. Now, the goal of the original UNet was cell segmentation, implemented for a very small data set, so in addition to adding heavy data augmentations and dropouts, some of the more specific design choices of the network may be seen as optional. So specifically, the use of a pixel-wise weighted loss function to emphasize accuracy of border pixels, the choice of use of valid convolutions, the specific tiling strategy used to apply these networks to very large microscopy images at test time. In our implementation that you will go through during the tutorial, for example, we implement same convolutions rather than valid convolutions, and I've also seen implementations with strided convolutions for downsampling and implementations with convolutional blocks with residuals. The key idea that always remains the same is that the decoder and encoder are symmetric and that skip connections are implemented between them. So the UNet remains a hugely popular method for segmentation, but in recent years there have been some suggestions of new components which can improve network performance, particularly for difficult recognition and segmentation tasks. So one example of these advantages is the incorporation of attention or transformer modules to attend to the most important locations in a scene. Again, these take inspiration from cognitive neuroscience, which has known for some time that human visual perception does not learn or attend to entire scenes, rather it automatically focuses on the most important parts of each scene required to perform a particular task. For example, this image demonstrates that objects attended to in the first 2 seconds of a person viewing a picture of a scene taken from a 1967 study by Alfred Yarbus. So one of the first examples of incorporating visual attention mechanisms was therefore proposed by a Google team in 2014. This proposed a recurrent approach composed of a glimpse network, which for a given location of L at time t-1, it uses a sensor network to crop the image at that location, but at multiple resolutions. These glimpses are then combined with the location and encoded into a single vector embedding representing the glimpse state, GT. The whole network is then implemented as a recurrence where the core network FH combines this glimpse encoding with the states learnt at the previous iteration to return a prediction for that glimpse, for example, an object classification, as well as a proposed next location to glimpse at. The whole network is trained with reinforcement learning. And therefore the goal, in a similar way to human vision, is to track across a scene, detecting important features or glimpses one at a time that can be considered most relevant for making a prediction from. This supports faster and more accurate predictions without requiring detailed processing of all parts of high-dimensional images. However, reinforcement learning is notoriously hard to train, so other approaches have instead incorporated concepts of soft attention. So here, rather than hard cropping out sections of the image to look at, a mask is learnt which blurs large parts of the image and focuses the attention of the network on a specific part. This concept was recently built into segmentation networks designed with medical imaging specifically in mind. So known as the attention UNet, this applies an attention gating module. which learns a saliency masking of the image so as to focus attention. So here, X are the input activations, and WG and WX here are gating coefficients to be learned. The output of each attention gate is some coefficients alpha, which element-wise multiply with the input feature maps to focus attention of the segmentation network at some specific location. Where in this figure we can see the attention coefficients in the second column and network feature activations before and after gating in the third and fourth columns. This network design avoids the need for cascaded networks, which previously had been considered standard for segmentation of difficult objects, due to the need to have one network to localize the object and another to segment. Note, another strategy for focusing on important regions of images can be achieved using spatial transformers. These are network modules which learn suitable augmentations, for example, crops, translations, rotations, or scales, by learning the parameters of a transformation using a localization network, and then mapping the result back to a regular grid in a reference frame. So like attention, these modules can be dropped into any other type of network, including classification, object recognition, and in principle segmentation to improve performance of the task. For example, in the paper they show that when training on a deformed MNIST dataset which they created, these transformers can learn to detect the object of interest and then resample it in focus within the reference grid to aid classification. So, in summary, segmentation networks implement encoder and decoder structures where encoders learn what is in the scene and decoders learn where objects are in the scene, so as to label all locations of that object. To do this, networks must be fully convolutional to support multi-resolution inputs and, importantly, upsampling through either transpose convolutions or up convolutions. UNet remains state-of-the-art, and the key to its success lies through its symmetric architecture and skip connections, which support mapping of high spatial frequencies through the network. However, further improvements might be gained through use of arguably soft attention and/or spatial transformers to focus the network on important regions. So that's it for video content for this session. Please complete the Keats quiz before moving on to the tutorial.